Okay, welcome to Geometry. I'm trying out a new live board, interactive whiteboard that can record this audio, so we're going to see how it works. We're talking today about, in section 2.1 of Geometry, about conditional statements and their converse. This is something you've seen if you've taken logic, and so some of it will be a repeat. Sometimes we might call things something a little different, just from one course to another. But we're going to start with conditional statements. A conditional statement is an if-then statement. An example is if you get all your work done, then you can meet your friends. There's a condition that you have to meet before you get the last part to happen. So every conditional statement has two parts. The hypothesis is the part that's following the if, and the conclusion is the part following the then. Sometimes in symbolic logic we would write P with an arrow and Q. This represents a conditional statement. It means P implies Q, or if P then Q. So when I have a conditional statement, the hypothesis that follows the if is going to be the part that we call P. The conclusion, the part that follows the then, will be the part we call Q. And so in the example we have above, you get all your work done is the hypothesis, and you can meet all your friends is the conclusion. Okay, so in each of these examples, we're going to take a regular sentence and try to write it as a conditional statement. So a rectangle has 4 right angles. I feel like I skipped something. I guess maybe not. I want to give this as an if-then statement. So I'm looking at the beginning part is a rectangle has 4 right angles. I'm going to take the rectangle part and I'm going to make that into the if, the hypothesis. So I would say if a figure is a rectangle, sorry. Clearly I'm still learning this. Okay, that's the first part. Then, and I'm going to put the last part of that sentence in as the conclusion, then it has 4 right angles. It's changing colors as we write. Okay, now I want you to try to do the same thing with part B, where it says a tiger is an animal. See if you can make that into an if-then statement. You can pause and write down your statement and then come back. Okay, so here the tiger is the first part. I'm going to say if something is a tiger, I didn't want to say if an animal is a tiger because the word animal is going to come at the end, so I'm using something. You could use creature if a creature is a tiger. Okay, then it is an animal. All right, now try part C. You're going to try to change an acute angle measures less than 90 degrees to be an if-then statement. Okay, on this one I would say if an angle is acute, then it measures less than 90 degrees. Okay, and you might have written something like if something is an acute angle, then it measures less than 90 degrees. That's okay too. Okay, now we're going to look at the truth values of conditional statements, and something that you've seen before are called counterexamples. That's if we are trying to say that a conditional is false, then we need to use a counterexample to show that, to prove that we're right. So in our first example, we have if it is February, then there are only 28 days in the month. Now, for something to have a true truth value, a conditional, if it's going to be true, anytime the hypothesis is true, then the conclusion has to be true. So in this first example, anytime it's February, then there has to only be 28 days in the month for this to be a true conditional statement. And so in this case, there is one time that I can think of where it could be February but not be 28 days in the month, and that would be a leap year. So the truth value here would be false, and our counterexample would be leap year, because then there are 29 days in February. Okay, now you practice on the next one. See if you can decide if it's true or false, and then if it's false, give a counterexample. So this is if you play a sport with a bat and a ball, then you play baseball. Okay, so this one is also false. The counterexample that I thought of was softball. So remember, for it to be false, the hypothesis needs to be true and the conclusion needs to be false. So if you play a sport with a bat and a ball, then you play baseball. But it could be true that if you played sport with a bat and a ball, then you're playing softball and not baseball. So that would make this conclusion false. Okay, the next thing we're going to do in this section are make Venn diagrams. So a Venn diagram is it's a visual representation of what we're reading. So the first example we're going to look at is if you live in Chicago, then you live in Illinois. So with a Venn diagram, let me get a picture up here. All right, I'm going to make a large blue oval. I want to fill it. Okay, this is going to represent a set of things that, if they were in that circle, they would belong to the set. So in this case, that's a larger set. We're also going to make a small oval inside. And so in the smaller oval will be another set of things, but they will also satisfy the condition of the things that are in the blue set. So we have to decide which set is larger, which one contains the other. And in this case, we have, if you live in Chicago, then you live in Illinois. The larger set, the set that would have more items or more things that satisfy the condition would be Illinois. So I would put residents of Illinois in the larger blue oval. Because there are more people that live in Illinois, they don't necessarily live in Chicago. Okay, and so the smaller set would be the residents of Chicago. I'm going to have to write small to fit that. And that goes inside the inner circle, because residents of Chicago are part of the larger set residents of Illinois. So it's a picture to illustrate what our conditional is saying. Now, you try to make a Venn diagram that represents if something is a Cocker Spaniel, then it is a dog. Okay, I'm trying to make my ovals. Okay, so in this case, the larger set, the one that has more things that satisfy its condition, would be a dog. So I'm going to write dogs in the blue circle. That would be the set that includes any kind of dog. It could be a lab, it could be a German Shepherd, it could be a mutt. Okay, but if something is a Cocker Spaniel, that's going to go into the smaller oval. Can't seem to spell today. Ooh. And I just covered it up. How'd that happen? Okay, there we go. Okay, so Cocker Spaniels are dogs, but they're the smaller set within that set of dogs. So basically with the Venn diagrams, you're looking for which one of these has the most in it and contains the smaller set as well. Okay, finally we're going to learn how to write the converse of a conditional. And so the converse, all it does is take the hypothesis and the conclusion, and it switches them. So instead of having P implies Q, we're going to have Q implies P, or if Q then P. So when I'm going to write the converse, I first want to identify the hypothesis and the conclusion, and then I want to swap those. So in the first one, if two lines intersect to form right angles, the part following the if is my P, that's the hypothesis. Then they are perpendicular, the part following the then is my conclusion. So what I'm going to do is I'm going to switch them and put the Q after the if and the P after the then. So if two lines are perpendicular, I'm going to use my symbol so I don't have to write as much. Okay, then they intersect to form right angles. All right, now I want you to try with the next one. If two lines are not parallel and do not intersect, then they are skew. I want you to write those as the converse. Okay, so here, two lines are not parallel and do not intersect. That is the hypothesis. They are skew is the conclusion. Okay, so I'm going to take these and swap them and say if two lines are skew, then they are not parallel and they do not intersect. Now notice, let's look at the truth values of these conditionals and their converse. Back on part A, if two lines intersect to form right angles, then they are perpendicular. If I tried to find a counterexample to show that the hypothesis was true and the conclusion was not true, then I would not be able to find one. So that one is true. The converse of it, if two lines are perpendicular, they intersect to form right angles, is also true. That's kind of clear just from the definition of perpendicular. Okay, then on part B, if two lines are not parallel and they do not intersect, then they are skew. That is also has a true truth value. Anytime the hypothesis is true, the conclusion is also true. And then if I look at the converse, then it is also true. So anytime two lines are skewed, then they're not parallel and they don't intersect. There's no counterexample that shows that those would be false. So in this case, the converse and its conditional, those are both true, but that's not always the case. Okay, so sometimes a conditional and its converse might have different truth values. Let's look at some examples. And the conditional here is if a figure is a square, then it has four sides. So I could write the converse. Again, I'm looking for my hypothesis and my conclusion. And then I'm swapping where they go. So I'll have if a figure has four sides, then it is a square. Okay, that's my converse. And then I want to see if the conditional and the converse are true or false. So the conditional, if a figure is a square, then it has four sides. That is true. There's not a counterexample where the figure is a square and it has some number of sides, four sides. So that part is true. Let's look at the converse. For the converse, it says if a figure has four sides, then it is a square. So there are some figures that have four sides that are not squares. So this one actually is false, and the counterexample, I'm going to say CE, would be, it could be a rectangle. A rectangle has four sides, but it's not a square, or a trapezoid, or something like that. A kite. Okay, now I want you to look at each of these examples. I want you to write the converse. I want you to determine the truth value of both the conditional and the converse. So pause and do that now. Okay, so on part A, my converse is going to be if two lines are parallel, then the lines do not intersect, or then they do not intersect. Notice that I'm rephrasing the P and the Q a little bit so that at the beginning, people still know I'm talking about two lines, because if I just say if they are parallel, then two lines don't intersect, it takes them a minute to figure out what I'm talking about. So I'm just switching the wording a little bit. Okay, now let's see. The conditional, if two lines do not intersect, then they are parallel. Is that true or false? Okay, it's true because there's not a counterexample that shows otherwise. The converse, if two lines are parallel, then they do not intersect. Oh wait, I'm sorry. This one was wrong. It was false at the beginning. Did y'all catch that? There is something else. If two lines do not intersect, they might not be parallel, they might be skew lines. They're in different planes. So that one's false. And the skew lines are my counterexample. Okay, maybe I should put an X. Alright, and then the converse, if two lines are parallel and they do not intersect, that one is true. So in this case, these have two different truth values. Okay, on the second part, B, if x equals 2, then the absolute value of x equals 2. I need to write the converse first. So I find my P and my Q, and I swap them. So I'm going to put if absolute value of x equals 2, then x equals 2. Okay, now on the first one, if x equals 2, then the absolute value of x equals 2. That one is true. It really is true this time. There's not a time that I could take the absolute value of 2 and get something different. But if I turn around the converse and I have if the absolute value of x equals 2, then x equals 2, this one is false because my counterexample would be if x is equal to negative 2. In that case, the absolute value of x would be 2, but the conclusion would not follow from that. Okay, so sometimes they're the same and sometimes they're different. That's what we're trying to make sure we see. Okay, that's it for this section. I think I must have left out a slide somewhere in here. I had gone out and typed them out, but the very first part, when you're identifying the conditional, from the conditional, the hypothesis and the conclusion, just make sure you're looking for what comes after the if. That's always your hypothesis. The conclusion is always what comes after then. And then when we're doing the converse, we're switching it so that it's Q first, Q implies P, or if Q, then P. That's how you're going to do your converse. Okay, good luck with your section, and let me know if you have any questions.